Howdy, welcome to stat626. My name is Simon Sheether, which will be no surprise to you, and it will be my great pleasure to be your instructor this semester. So let's start off with some expectations. What you can expect from me is I'll work very hard to give clear explanations. I will provide some math, but I won't rely on just mathematics to explain how models work. You'll see that we will totally look at real-world examples. Some things that will turn out to be relatively straightforward to predict, and other things that are very difficult to predict, and everything in between. You will find that I am very enthusiastic about the subject. In particular, we get a chance to predict the future. So in all the data sets, the last few data points are used as a holdout sample, and we get to see how our model works by looking at the difference between the predictions and the actuals, i.e. the prediction errors. And you'll see I get very excited when I do well, and I get even more excited when I don't do well. I have my usual commitment to help. I'm going to work as hard as possible to make the lowest score as high as possible. So if you do the homeworks, the group homeworks, the group project, the midterm and the final, and you attend class and participate, I will work in every way possible to get you the highest score. You'll see that I have a genuine response to feedback. I'll explain what I've changed since last year, and naturally I will abide by Texas A&M rules. Having been a department head, I know those rules pretty well, and I'm bound to follow them. What do I expect from you? Active participation in class, active participation in breakouts, and active participation on the discussion board. I don't believe that will be a problem for you guys. You've been incredible in terms of participation. This is the third time I've taught this course, and as you'll see, I update the data sets every year to 2017 in this case, but it's now time to produce a draft of a book. So what will really help me is if you have a question as the class goes on, that you type it in the chat box, the text chat box, and send it that way, because then I can keep a repository of questions, and that will really help me revise the material. I also expect from you continuous learning. This is a subject where every week builds on the previous weeks. It's a way to think completely differently to what you've done in the past. This term stationarity will drive you crazy until you get on board with it. So it's very important in the early weeks that you stay up to date. If there's something you don't understand in the early weeks, then we're going to have problems, serious problems later on. And I will emphasize this with some of the early topics as we go through. If you have an issue, I ask you to seek help as soon as it is needed. So I remember fondly from 608, you guys broke the record for the most discussion questions. So I look forward to the record being broken in 626. Please post the questions on the discussion board. I get hundreds of emails every day, and they just get lost if you send them to me that way. I'm interested always in honest feedback. If you've got a suggestion, please send it to me. And if there's any questions or appeals about grades, let's put these in writing so we can solve those in an amicable way. So let's go to the course outline. What we're focusing on are tools and techniques for building, using, and interpreting valid models for time series. So we're going to build a model, and then we're going to use a model to predict the future, and then we're going to interpret what the predictions are. In particular, sometimes the quality of the predictions is not very good. And it's good to know when you do well and when you don't do well. Some things are just hard to predict. And it turns out other things are relatively straightforward to predict. And we're going to look at everything in between. And we will use real-world examples. If you look at just the examples we're going to use in the first week, I expect you'll find them pretty interesting. So, at the end of this course, the first thing, what you should be able to do first is prepare time series data for model fitting. So, we'll see that time series methods assume that the data is put in time order. So if X is the time variable, that goes from the furthest back date to the most recent. And then what do we do with missing values, etc., etc. Starting in the very first week, we're going to look at the properties of stationarity versus trend and seasonality. So we all know what trend is. It means something trends up if it tends to go up, something trends down if it tends to go down. And seasonality, as they say in Australia, you sell more meat pies in the wintertime than you do in the summer. In the third week, we'll talk about, in particular, outliers and level shifts, how to identify them and what to do once we've identified them. A level shift is a complete change in the series. So if a company buys another company, that should shift the income for that company upwards in a step function. Again, we'll look at that. So what we're about is fitting appropriate models, and we will look at a wide variety of business settings. The great news about publicly listed companies is they have to make public a lot of their data. We'll work a lot on interpreting the output. So what does that model tell us? What does it tell us? We're going to identify weaknesses in models and formulate ways to overcome them. So in the first few weeks, we'll produce relatively simple models, and in the last few weeks, we will get much more sophisticated. We want to make valid predictions of future values. A prediction is only valid if the model is valid, and we will draw business conclusions on the basis of the fitted models. And then obviously we will recommend business actions. What should we do differently on the basis of this? So here's the topic list. Today in topic 1, we're doing an overview, and that's what we're doing right now, in an introduction. And the main ideas we'll talk about are autocorrelation, correlation of a time series with itself, self or autocorrelation. Stationarity has 3 conditions we'll see. If something's not stationary, it may have a trend, or it may have seasonality, or it may have both. And then next week, we'll look at autoregressive models. We'll call them AR models. We'll look then at moving average models. We'll call them MA models. Then we'll look at autoregressive moving average, or ARMA models. And then we'll look at autoregressive integrated moving average models called ARIMA models. So ARIMA models are a very rich class. They include AR models, moving average models, and this integration business that we'll get onto. Then we'll talk about exponential smoothing, and I will rant and rave like a lunatic as I do. Exponential smoothing is very popular in business, and you'll see that I'm not a real big fan. I'm not a real big fan, but you'll see. You can imagine I'm going to go crazy. Then we'll look at regression models with autocorrelated errors. That was the last topic in 608. And what we did was assume that the errors were autoregressive 1. What happens if there's something other than autoregressive 1? Well, that's what we're going to do in topic 7. In topic 8, we're going to use a relatively new package called SAS Forecast Studio, which automatically fits models to data. So it's like an artificial intelligence system. and we'll look at when it does well and when it does poorly. And I'll show you how, when I was a kid, I used to love watching Superman, and Superman could beat anything except kryptonite. Well, I know the kryptonite for SAS Forecast Studio. Now, it beats some of my models, and I get really cranky, And you'll see, and I fess up to them, I will have it in the class where it beats my model, I'll get really cranky. Topic 9, we get really advanced. We're going to look at models for more than one time series. A transfer function model. So we've already had a presentation in class from one of last year's graduates where he used a transfer function model. And I'm going to show you a simple example of it today in the introduction so you can get an idea. And then the other one is when we have multiple time series that are related to each other, multivariate time series. I'm going to put an example of that in front of you as well. And then finally at the end in week 10, we'll put it all together. So, if you look at the syllabus, there are homeworks which are to be done in groups. There was going to be a homework for week 1. Instead, we're going to do this as exercises. You don't have to turn it in. And what I'm going to do is most Mondays, when my schedule permits, at 6 p.m., I'm going to have online office hours. Dr. Jones told me how successful his online office hours are, so I'm going to do that. And we'll talk more about what I plan to do in next Mondays. Now, there are some Mondays when I will be indisposed, and we will do the office hours on the Wednesdays. I will give you plenty of notice. I'm very proud of my standing in the academic community, and that means I get invited to do things. And I can't say no to some of these things because it'll get me out of the loop. So there's a couple of weeks that I will be traveling, but we'll get to that. So there'll be a midterm exam, Tuesday, October 10. As always, I will put up the past exams. They're like my children, and the answers. We'll get to that in due course, but basically the questions will be a lot like the homework questions, and you will be asked, like in 608, to use JUMP and or SAS to fit a time series model and interpret the output. And you'll hear when we get to it that one of the students last year got a better model than I did on the exam. So never say never. Then there'll be a final exam on October 12. But the thing that I'm really delighted by is that there's a project, a term project where you give a presentation. They'll be short and sweet. And I ask you to submit a proposal. I want a proposal because I want to make sure that the project is not too trivial, but I also want to make sure that it is feasible. I have a really good idea about what's feasible and what's not. So here's the term project. Again, you do it in groups. So let's go back to the previous slide. So my whole thinking about teaching in executive settings is that there are plenty of people in each group that are very smart and very talented that bring different experience to bear. So you learn a lot doing the homeworks and the project from each other. So that's why I always have those as group. But if you remember me from 608, I love making up exams. I love making up exams. And no one's ever got 100% on my final in this class. Never. Someone got really close, but nobody's gotten 100%. So if you're going to be a passenger, the bus is going to crash at the midterm and be burnt and destroyed at the final exam. So let's talk about the project. You have to find your own problem, right? I could give out problems. No. You're in the 4th semester of a professional master's program. I can give advice about where to look, but I want you to have your own data set. And in the past, one of the team members has volunteered a series from their own work. So, Department of Social Security inquiries, butterball turkey sales, Home Depot sales. There are lots of things possible. So I want you to build two competing models. We'll see throughout this course, one of the things that we stress is there isn't a single right model. It's always a good idea to put ahead two competitive models head to head and in the end choose between them. Sometimes you might say, well, A and B are pretty close. Or you might say, well, model A is clearly inferior to model B. Interpret your model. Identify weaknesses in your models and formulate ways to overcome them. Make valid predictions of future values. I'm going to be really interested in your prediction error. And draw business conclusions. Recommend business actions. And those points are really important. If you just do a nerdy time series model and I'm left saying, so what? What are we going to do differently? That will not excite me. And then decide which of the models should be preferred. Prepare your answers. The report should be no longer than 10 pages. But you can have as many appendices that you like, as long as the appendices are numbered and referred to in the report. So if you turn in 60 pages and I don't see a single reference to a figure or a page in the appendix, that's great, I won't even look at it. Please ensure that you explain the steps you took to produce your final model. Not, we fitted 126 models between us and we like this one the best. Oh, don't get me cranky. Please don't wind me up. That's not a good way to do things. I want to understand the model fitting logic that you used. The report has to be fully self-contained. If there's some terminology, I don't know a lot about turkeys, having grown up in Australia, not a big deal there. So if there's actually an important differentiation between frozen turkeys and fresh turkeys, you better explain that to me. And then, of course, give me an executive summary. I'm always blown away by these projects and I look forward to reading yours. So there is a textbook and we will follow the notation in the book. It's the best one I can find because it's not a theory book. As the title suggests, time series analysis and forecasting by example. It has lots of good examples. It has more words than what I do, but here's the deal. I'm going to try and turn my class notes into a book. So I'm going to put to you that if you look at the class notes and make notes of what's said in class, that should be a more thorough reference than that particular book. We will use SAS. The latest one is 9.4. We will use JUMP. The latest one is JUMP Pro 13. You'll see that JUMP gets us started. If we want to fit a basic time series model, it's great. If we have anything more than a relatively straightforward model, we have to use SAS. So if we identify lots of outliers, there's no straightforward way in JUMP to fit a model that identifies first and then accommodates the outliers. So there are two broad types of modeling. You remember this slide in 608? Explanatory modeling is the process of building and applying a model that is interpretable. The most important word there is interpretable. So, in other words, which variables have a meaning effect on the outcome variables, as well as understanding each of these effects. So my experience in the business world is no one will use a model, no senior person will get on board with your model unless they can understand it. If they're going to make changes on the basis of your model, do more advertising, lower costs, change the parameters in this particular oil well. They want to understand why that works. So The second part is predictive modeling, which is all about trying to predict future observations. Here we're interested in just the predictions. So in Arnold Zellner's famous thing that I love, keep it sophisticatedly simple. Sophisticated enough that all of the variables that you believe affect the outcome are in there, and simple enough that the model is not so complicated that it takes 3 blackboards to write it on. So we're going to start with looking at gasoline prices. And there's a wonderful site which has all of these, and we're going to go back to 2009. And we're going to look at the average weekly price. Can we predict the average weekly price? So, given this is a recording, I'm not going to go through all the steps in Jump because I'm not showing you live. What I'm going to do is just talk to the slides. And what I suggest you do when you play this back is you have the video on half of your screen and you have Jump on the other half of the screen, and you follow the steps that we go through and keep up with me. That means the video will be much shorter. You don't want to listen to me to drone on for 3 hours, even with my beautiful Australian accent. And you can do this at your own pace. So if you're very good with manipulating things in Jump, you'll do this quickly. If you're relearning how this goes, then you can stop the video and start again. So we're going back to 2009, after the last major recession, and we're looking at the average unleaded price of regular gasoline in conventional areas. And you see that we have 451 rows to build the model, and we have kept back 8 rows. So we want to use up until the end of July, end of June, excuse me, up until the end of June, the 6 months, in order to predict the results for July and August. It's like 8 points. So we've held back those 8 points. So what I did was go rows and just hide those points. Now, what we're going to start by doing is doing a model of not the price, but the change in price. How much did gasoline change? How much did its price change week on week? So, for instance, if we look at the first 2 weeks of 2009, on the 5th of January, it was $1.67.2. The data is recorded to 3 decimal places because it's an average. The next week, on the 12th of January 2009, it was $1.77.2. So that's a 10% change in price. Week 2 minus week 1 is a 10% change. If you go from the 19th of January to the 26th, $1.83.2 to $1.81.3, that's a reduction of 1.9 cents. And because we've put the notation as dollars and cents, it puts parentheses around it. We all remember that beautiful thing from accounting. So here's a plot of the series. And right now, you're looking at it and you think, well, I'm not sure what I see. But believe me, by the midterm, you'll be talking in a rapid fashion. I see all these beautiful things in that series. As I say, things are popping out of my porridge. And we're just going to go through all the things that we see. We're going to look at that example later today. Let's look at example number 2. Berkshire Hathaway. Warren Buffett's company. Man's a bit of a genius when it comes to making money. And we're going to look at quarterly data. So publicly listed companies report earnings on a quarterly basis. It's easy to find it publicly. We're going to look from 2000 to 2016 quarter 4 in order to predict the first 2 quarters of 2017. There's an example from the annual report. You can see that in the first quarter of 2016, these things are in thousands, so it was 52 million in revenue. So here's a plot. What do we see? Well, the first thing I see is an increasing trend. Mr. Buffett is good at making money, and he's even better at making money. It kind of goes up. And in fact, it's really hard to see anything else other than the trend at this point, because the trend is so strong. Next, we'll look at turnpike transactions, toll roads. I'm fascinated by the toll business. Right from in 2001, I taught executive MBA students at NYU, and one of the students did a project on toll road revenue from the Easy Pass system. And I've never forgotten that. It was really, really interesting. I learned a whole bunch of stuff about toll revenue that I really didn't know before. And it's easy to pull off. I'm not sure what happened. They've only just posted the report for April. Excuse me, it's the end of August. What happened to May and June? So I'm not sure, but we've got up until the end of April. Now, here's the transactions. Wow, look at those. Look at the seasonality. They're high at one time of the year and low at other times of the year. And let's think about a cookie cutter mentality. If you cut out the first year, you actually got this on a piece of paper and got scissors and cut the first year out, and then looked at the first year versus the second, the first year versus the third, etc., it wouldn't change that much. Until the last couple of years, it seems to have lifted up a little bit. So that's transactions. That's the number of vehicles through the toll booths. 9 million they're up to. Wow. Let's have a look at the fare revenue. This is a good business. This thing has an increasing trend. The seasonality is still apparent, but there's an increasing trend. Now, presumably the reason for that is they keep putting up the price. They haven't changed the number of vehicles much, but they've presumably put up the price. So in 2007, the maximum was about $9 million. In 2016, the maximum is more than $14 million. Again, a good little earner. So I showed you 4 series there. The change in price of weekly gasoline, Warren Buffett's Berkshire Hathaway quarterly sales, main turnpike transactions, and main turnpike revenue. One of those series turns out to be stationary and the other 3 are non-stationary. Let's look at the properties of stationary. And this is going to be the mantra. Every time you see a time series, you're going to want to understand whether it's stationary. It's the most important thing. If you get this wrong, you're in more trouble than the early settlers of Australia, because there is no way to build a valid model from a non-stationary series using the techniques that we learn. So a series is weekly stationary if the following conditions hold. The expected value of y equals mu, i.e. the mean of the series is constant. We can't have a roller coaster, we can't have that seasonality, so that violates that. The second one is the variance of y is a constant for all t. The variability doesn't increase. Sometimes the variability of sales increases as we get more sales. And then the correlation between yt and yt minus s. So s is the number of lags before. So let's take s equals 1. The correlation between yt and yt minus 1 is constant for all values of t. So the correlation structure doesn't change over the series. And again, looking at the time series plot helps us with that a lot. So in other words, yt is weekly stationary if it has a constant mean, constant variance, and a correlation structure which does not change over the life of the time series. throughout the course, we'll assume a time series stationary if it's weakly stationary. A time series is non-stationary if any of the three conditions do not hold. Throughout this course, we shall first perform steps to produce a stationary time series and only build models for stationary time series. Only. We'll see that there's plenty of ways to turn a non-stationary series into a stationary one, and then we can do our model building. Now, it's possible to model some non-stationary series using advanced techniques. Well, good luck. There are PhD courses on this, but that's above what we do. Again, you'll see we can fit time series for essentially everything using this stationarity idea. So, having looked at the time series plot, the next thing we always look at is a plot of autocorrelation. So, the correlation between yt and yt minus 1. The correlation between yt and yt minus 2. And again, if we're worried about outliers, we should plot yt versus yt minus 1. This week's value versus last week's value. Yt versus yt minus 2, this week's value versus the value 2 weeks ago, etc. So, here's the data. You'll notice that rows 444 through to 451 have been hidden and excluded. They are the values from early July until the end of August. That's what we're trying to predict. So, the first thing we can do before we even use the time series module is we can use the formula command in JUMP. So we go column new, we get a new column, we're going to enter the name lec1 change in price, we're going to click on column properties and go to formula, we're going to go to row and click on lag, and then we get lec1 change in price. So here's a plot, top right, which shows the change in price. What's the most recent change in price versus what was the change in price a week ago? And if you look, there's a mildly positive correlation of about 0.52. 0.52. That's moderately strong. We'll see that we'd like a little bit stronger than that, but we can work with that. And then the correlation between yt and yt minus 2, the change in price this week versus the change in price 2 weeks ago is much less strong. It's 0.27, and you can see the points in the plot actually spread out. So let's go back and look at the time series plot. When I look at the time series plot, if I tell you that last week's value was above the mean, then typically this week's value is above the mean. So find a value above the mean. So if you look at the point that I've highlighted, the points immediately after it are above the mean. If you look at the next point I highlight or I circle, the points around it are typically below the mean. So when you see points that are above the mean and they're followed by points above the mean, and points below the mean are followed by points below the mean, that's the evidence of positive autocorrelation. If the autocorrelation was really strong and positive, you'd see a lot of points above the mean and a lot of points below the mean. So we're going to look at graphical ways to check the conditions for stationarity. The first condition, you remember, is the mean is constant. The mean is constant, so that what I'm going to do there is use fit y by x, flexible, and choose a kernel smoother. Turns out a kernel smoother is just a non-parametric function, regression function, which says I'm going to estimate the curve by what happens in the region around that curve, by a series of small curves just joined up. Now, if you have a look at the red curve here that's produced, it's relatively horizontal, right? It's relatively horizontal. And the great news about kernel estimates is they still work well when the data are autocorrelated. We don't have a problem with that. It turns out two of our faculty members here at Texas A&M, Dr. Welly and Dr. Hart, actually produced the theory for this in the 1980s, that this works, and their work is still used today. I'm very proud of those guys. So, it's a bit loosey-goosey. We just look at the curve, and loosey-goosey we say, based on experience, the red curve is relatively flat. So I'm going to say that condition 1, the constant mean, holds at least approximately. The second condition is about variability, so we're going to save the residuals from the red curve and plot the residuals using Graph Builder versus the date and see if the spread stays about the same. And as much as we did in 608, if you draw two horizontal lines, that's not bad. And two horizontal lines up here, the points are about equally variable as you move across dates. So I'm going to say condition number 2 holds. That's the change in price seems to be stationary in terms of having constant variance. Now, we're going to look at the correlation function, the autocorrelation function, over 55 lags. And I chose 55 lags because in particular, I'm interested in lag 52. What happened 52 weeks ago? We'll see with weekly data, we're going to look at week 52, week 104, etc., to see if there's an annual effect. There is in many, many time series. Now, the thing that's weird, but all of them do, is lag 0. That's the correlation of y at time t with y at time t, and that's 1. Okay, hello, we all know that. I'm not sure why they put that, but they always have. Then we have 0.5248. That's the correlation between y at time t, this week's change in price versus last week's change in price. 0.27 is the correlation between this week's change in price and 2 weeks ago. You can see down to, there's lag 7, the correlation is 0.0305. That's pretty small. And then 52, it bounces back to about 0.2. Now, if you look at the plots, I don't see any big outliers that will affect the correlation. Remember, I'm not a fan of correlation. I only look at it when the data is relatively symmetric without outliers, and all those plots look like that. We'll see that these blue lines really help us interpret things, but we're getting ahead of ourselves with what they mean at this point. So I'm going to show you how to do that. So for time series in Jump 13, we go to the Analyze menu. We go to Specialized Modeling. They've got an expanded menu in Jump. Specialized Modeling in time series. We have to tell it what Y is, that's change in price. We have to tell it what X is, that's the date. And we have to tell it, if we want to change, how many lags of the autocorrelation do we want to look. The default is 25. We want more than 25 because we want to be able to look back a year ago. Now, then you get the time series output, and if you want to show the lag plots on the previous slide, you go to red triangle. We all love red triangle. It says if I want anything fancy out of the time series, I'm going to red triangle and I'm going to show the lag plot. Now, here's the trickiest thing we do this evening. And if we were in class, There'd be lots of questions. We'd get all real excited and we'd go back and forth. The one good thing about recording is I'm going to try and go through the whole 9 yards and explain what I did, why I did it. And then if we have any questions, I really look forward to going through this at office hours on Monday. So what I did was say, okay, I want to see if the structure of change in price changes over time. So what I did was color each point depending on what year it is. So the 2009 points, I put all them in blue, right through to the 2017, I put in turquoise. I don't know if that's how you say it in this country, but that's how you say it where I grew up, and everything in between. So your job now is to look at the different colors and say, do those plots look different? Do they look different? Well, it's a bit hard in the first week in time series to see that, but let me tell you, I'm old and I'm pretty confident that they look pretty similar. We could do this another way, and we're going to do that next. Is what I'm going to do is I'm going to plot Y, change in price, YT, versus YT minus 1, separately for each year. And I bet you're thinking, there'd be a question already in class, why did I pick YT minus 1? Well, that was the one that had the highest correlation. Remember the correlation between Y and YT minus 1 was about 0.5, and it went down after that. So let's look at the variables that have the strongest relationship. And I want to ask myself, is the slope of that line, the relationship between YT and YT minus 1, does that differ across year? Well, we can fit actually a regression model to do that. So again, I used jump, and I fitted a model where the predictors are lag1 change in price, YT minus 1, year, and then the interaction between lag1 change in price and year. And the interaction tells you, are the slopes of those lines different? If there's an interaction that says the effect of lag1 differs depending on the year, and hello, the p-value is 0.206. So that's saying, assuming a valid model, at this point there'll be all these questions about valid models, I'll get to that in a minute. Assuming this is a valid model, it says that the relationship between lag1 change in price and change in price is consistent, does not differ significantly across each year in the day. There's a whole bunch of assumptions we've made there, and when we get to fitting regression models with time series errors, we can revisit that then. So right now you just have to trust me. So in summary, the 3 dot points, the first column shows its time series plot colored by year. The second column shows a plot of YT versus YT minus 1 for each year. The third column shows the results of a test of whether the slopes of the lines for each year differ. So we conclude here that the correlation structure does not appear to change over time. So I actually show you on this slide how to do that last model. I'll let you follow that yourself. It's exciting when you get to push run. And here's the data again. So it turns out I'm old and I love looking at these plots. And I could tell you, yep, by just looking at the plot, the mean looks relatively constant, the variability looks relatively constant, and the correlation structure doesn't appear to change over time. So we're going to assume that YT, the change in price, is stationary. Next week, we're going to develop a model for this change in price. Okay, so we start with something easy peasy, where everything is stationary. Let's look at something that's not stationary. So here's our revenue in millions of dollars for Berkshire Hathaway on a quarterly basis versus time. Here's the mean constant. No. The mean increases over time. So condition 1 for stationarity is not hold, right? For us to fit a time series model, we're going to have to account for that trend somehow, and we will. There are the residuals from the local smoother. They look relatively like they have relatively constant variability. Somebody once said to me, oh, this plot changes every year because I get more data. Looks like a bit of a fish. I'm not sure about that, but I'm not looking at animal shapes. I'm looking to see if the variability is constant, and it looks relatively constant. Then here's a plot of the autocorrelation function. Look at the lag, the correlation between the revenue this quarter versus the revenue last quarter. It's 0.9342. Whoa, that's strong. That's good. But have a look at these autocorrelations. 0.93, 0.88, 0.84, 0.80, 0.76, 0.70, 0.65, 0.62 to 2 decimal places. The autocorrelation function takes many lags to die out. And we'll see that that's again popping out of your porridge and saying, excuse me, this is not a stationary time series. If we have a stationary time series, we want the autocorrelation function to die out after a relatively small number of lags. But we'll get to that. So, we have found that the mean of the Berkshire Hathaway quarterly revenue increases over time, so we cannot proceed assuming that YT is stationary. What shall we do instead? Well, as you know, my favorite first step is worry. Well, clearly we have to take account of that trend. We need to do something to take account of the trend, and we'll actually look at that in week 3 or week 4. And we will fit multiple models to this Berkshire Hathaway quarterly revenue and compare them. Let's look at the main turnpike transactions. And here I'm going to have a moderately large alpha. It's what the default was in jump. I'm going to start with that. So what that says, it's fitting curves over many months, not over a small number of months, and paste them together. If I look at that red line, it looks pretty flat until 2014. And then the transactions appear to go up. So the mean looks constant from 2007 to 2014, and then it seems to go up almost like a straight line. Interesting. I wonder what happened. If we look at the residuals, the seasonality is apparent, but again, the variability is relatively constant over time. Now, have a look at the autocorrelation function. It looks like Christmas trees. There's a positive Christmas tree, a negative Christmas tree, a positive one and a negative one. Oh, I get so excited when I see that. It brings a little tear to my eye. That's saying we have stationarity. We have not stationarity, we have seasonality. We have very strong seasonality. Very strong. So have a look at the lag plots. The transactions, so the very first plot with lag 1. So there's a high correlation between the turnpike transactions in the current month and the latter months. The correlation is about 0.7583. Have a look after 6 months. The correlation is minus 0.7371. Negative, we have a negative relationship. Right? So if I told you something was high 6 months ago, it's going to be low in 6 months' time. And then have a look at the correlation between transactions and what happened 12 months ago. The correlation there is 0.85. It's actually the strongest correlation of any value on this chart. So the strongest correlation between transactions is not what happened last month, but what happens exactly 12 months ago. January's like January, December's like December, etc. So we have seasonality. Most things are seasonal. We'll look next week that there's a product that you all know and love, and I bet use for relaxation, which is not seasonal. But essentially everything else is seasonal, and we're going to have to learn how to deal with seasonality. Now, how do you check whether something's seasonal when it's not so obvious as the Christmas trees? What you can do with these plots, which they're explained in the book, page 113, they give examples. So what I've done is plot transactions as Y, and then I've plotted the months across the bottom, and each of these curves is a different year. So 2016 has the highest transactions, you remember. It increased in the last couple of years. It's that purpley pink curve that's up the top. But again, have a look at the patterns. If you're in July and August, you typically have the highest number of transactions. More cars go through the turnpike in the summer than they do in the winter, January and February. Gee, that's really interesting. I wouldn't have thought in a place like Maine, there's such a difference. So if you look, in the wintertime, there's around between 4,000 and 5,500 transactions. In the summertime, there's about double that. Now, you could do this a different way, and I like to look at it both ways. This is plotting year on the horizontal axis and then plotting months. So notice August is this kind of, nasty green color. Reminds me of something, but I'm not going to tell you. The deal with involving small children, but we won't go there. But have a look that August is always on top the highest value for every year, followed by July. So I actually like to look at both of those. And it's clear from these plots there is seasonality. So I have looked, and we'll look at some case studies where the autocorrelation function wasn't that convincing, but these plots said, excuse me, you need to worry about seasonality. Then what happens if we have a low alpha? So I'm going to change this smoothness alpha down to the lowest value to allow is 0.025. So that says, for those who are really interested, it's not really important, but if you're really interested, we're going to look at neighborhoods around 2.5% of the data. So if we had 0.5, if we want to estimate the value of the red curve at a value, we're going to look 25% of the way in one direction of time and 25% of the way in the other direction of time, and have this smoothness to be 50%. If the smoothness is 2.5%, we look 1.25% in one way and 1.25% in the other way. And so we've got very narrow intervals. And guess what? The red curve follows the up and down in the data. And it's very clear that there's strong seasonality. So what should we do? Well, we better figure out how to cope with seasonality. And that doesn't come until after the midterm exam. But we will look at it. Let's look at the revenue. They were transactions. If we do our kernel regression estimate, our local smoother, look at the red curve. Goes up pretty linearly. The mean increases over time if we ignore the seasonality. The variability is pretty constant. Don't worry, in the Monday nights Q&A, I'm going to show you something that doesn't have constant variability. We can see everything's possible. And then look, oh, I don't have my positive and negative Christmas trees. I have them all pointing in the one direction. This brings a different tear to my eye. What is going on? And again, we see a strong correlation between YT and YT minus 1. That's the largest correlation this time, 0.8274 versus what happened 12 months ago. It's really interesting. So what's the difference? In the first series, there's no trend. In the second series, look at the trend. So we've really got two things going on that autocorrelation function. There's a trend up and seasonality. And so whenever there's a trend up and seasonality, my experience tells me you're going to get the Christmas trees pointing in one direction. If there's seasonality and no trend, you're going to get the positive and the negative Christmas trees. Believe me, before at the end of the semester, you'll smile and go, oh, I get it now. And again, here are our plots, our interaction plots. where we plot the fare revenue against month for different years, and our friend 2016, as we expect, comes out on top. Or we can plot the fare revenue versus year for different months, and again August mostly comes out on top, July and August. So there's clearly strong seasonality in this data. And if we use a small alpha again, 0.025, yep, we get a plot of a red curve which copes with the increasing trend and copes with the seasonality. So we've got two things to worry about here, a trend and seasonality. It's interesting. We will be able to cope with both. Okay. Hotels. We had somebody who worked in the hotel business that just graduated, and their project, which I supervised or I coached, was about the average daily room rate in hotels in New York City, and also what was the average daily rate for Airbnb, trying to understand whether there's competition between those two or are they complementary. When it's a busy time of the year, do they both do well? Anyway, that's the big league. Let's start in the little league, and we're going to look at Vancouver. And you'll see why I picked Vancouver, Canada in a minute, and this is monthly average daily rate. So on average, how much do they charge each month at hotels in Vancouver? And here's a plot of the time series, and you go, oh, what happened? In early 2010, the room rate was $240. Oh my golly gosh. And that was the month of the Winter Olympics. So that's a giant outlier. Now, I laugh when I look at time series books and they don't tell you how to fit a model in the presence of outliers, because most business data have outliers. So if you have a very small number of outliers, here's what we used to do in the old days. You'd remove the outlier and replace it by a missing value, and then refit the time series and then estimate the outlier. I was never happy with that. It always bothered me. It would be much better if we could do the model fitting which accommodated for the outlier at the same time as fit the time series model. And that's what we're going to do. We're going to call this an additive outlier. I'm going to talk about those as soon as next week. An additive outlier means that something was added to the data for one period and then it went away. So here is our seasonality. Here, well, the other thing we should have said was there's clearly seasonality. In the summer, the room rates are higher than in the winter. And because there's an increasing trend, again, we see the autocorrelation function have these Christmas trees all pointing in the one direction. And have a look at these lag plots. Oh, this brings a little tear to my eye. Have a look at these points over here. They correspond, both correspond to the outlier. Think about it. You've got YT and YT minus 1. If YT is high, that's the Winter Olympics month. YT minus 1 is okay. That's one of them. What if you've got what the month after the Olympics? That's okay. But the month before, YT minus 1 is all right. So you get the outliers in both directions. So you have to really be careful. What we're effectively doing is assuming a straight line in this data. Now, if these things balance, we're sort of okay if we can adjust for them. We'll see when we look at level shifts, the world is a bit more complicated. And again, we do our interaction plots versus month and versus year. And we see that there's the Winter Olympics, the big spike. But have a look here in the summer. The largest values generally are in the sum. And you can do it the other way, over year versus month. And there you go. So there's strong seasonality available, evident in the data with an outlier. And in a few weeks, we're going to smile because we won't find this that difficult. We won't find this that difficult. Okay, and one of the things I'm very proud of, and some of my colleagues at the university said I was crazy, and that made me even more determined, because if you do the Master of Science in Statistics course in time series at this university, they will at best mention transfer functions and say, this is a bit more advanced than we can do in a first master's level course. Come back again. Well, no. We're going to bite the bullet and we're going to teach you how to use transfer functions, because in business, they appear everywhere. So what we want to do here is we want to predict gasoline prices from oil prices. Sounds reasonable? If the oil price has gone up for a few weeks, well, gasoline should go up. If the oil price has gone down for a few weeks, gasoline should go down. So there's the oil price. Now, if I could predict oil price, I'd be smoking cigars in silk pajamas, drinking the best wine I can find. So we'll see that that's a really hard series to predict, but we'll have a go. Anyway, it's called the transfer function because we're trying to predict the output, the price of unleaded gasoline each week, from the input, the weekly oil price. We're trying to predict a time series from a time series. Oh, that's exciting. That's very exciting. And the project that co-won the prize for the best project that I'm hoping you'll get to hear about this semester from the author himself actually did a transfer function with two inputs, with actually two time series, and that's really been a thrill seeker. So you look at those two pictures and they look pretty similar. The thing is there a lag? Does it take a few weeks from when the oil price goes down for the gasoline price to go down? Or is it immediate? I don't know. We're going to have to figure that out. But it turns out we're going to have to know and love the properties of each of these time series before we actually try and model one from the other. And then we'll look at multivariate time series. You know, they say, Sheila, you're crazy to do transfer functions, and now you're going to actually look at multivariate? I go, yes, sir. Yes, ma'am. Here we go. And we had somebody last year from Home Depot, so we got some expert advice in the class. Home Depot and Lowe's are great competitors, and this is a multivariate time series. They should change at the same time. Think about transfer functions. Oil changes in price first and then affects gasoline. That's why it's a transfer function. The properties of oil price transfer to the property of gasoline prices. That's not what we're doing here. What we're doing here is saying, hey, if this is a really good market for Home Depot, it should be a really good market for Lowe's. If this is really a terrible market for Lowe's, it should be a really terrible market for Home Depot. And we have a look at the plots, and they sort of look similar, but have a look. There's increasing variability. Look at the very low variability here and the much higher variability here. Again, if we were doing this using the previous methodology, we'd fit a local smoother, a kernel function to that. You would find a nice smooth curve and look at the residuals, and the residuals get more variable as time goes on. Let's log transform sales. And when I saw this, I was so excited, because have a look how constant the variability is. Looks like I made up the data. I didn't make up the data. This is real data. And we're going to fit a model, and yeah, that is hard. When you've got two series, it's not easy, but again, we'll do decently. We'll do decently. And we're going to model. What we're going to do is we'll develop a model for Home Depot and a separate model for Lowe's. They're our benchmarks. And then we're going to develop a model for them jointly. And does the joint model beat the separate models? Sometimes it does, sometimes it doesn't. All right. So we've talked a lot about what we're going to do in the future. Let's actually do something today. So, a few years ago, just about every graduate student in finance thought that they could come up with a good time series model for exchange rates. And there's the age-old story. How do you end up with a small fortune? You start with a real big one and you try and predict exchange rates and buy futures. So, as we'll see, please be careful doing this. Please be careful doing this. So we want to model the daily exchange rate between euros and US dollars. I love going to Europe on vacation. Paris is my favorite city in the world. And we're going to go way back to 2006, and this is daily data. Wow. There's the time series. It's been all over the place. I remember in 2008 when I paid $1.60 for a euro. These days it's just a bit over $1.10. Now when I look at that series, I start talking to myself, but I'm going to control myself because I don't want to ruin the story. The first thing, does the mean look constant? No, 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 no. It's up and down all over the place, right? Up and down all over the place. Long periods above the mean, some periods below the mean. That's not a constant mean. Let's have a look at the autocorrelation function. Excuse me? The correlation starts at 0.9962. So the correlation between today's exchange rate and yesterday's is 0.9962. 25 days ago and today is 0.9543. So the autocorrelation doesn't die out. Oh no. This is a telltale sign of non-stationarity, but it's also a telltale sign of what we will discover is called a random walk model. If you want to go to a dinner party and talk nerdy, talk about random walk models. But be careful. So let's look at the definition of a random walk model. It turns out it's one of the easiest time series. It turns out we can fit this model in our heads. Again, you can be really nerdy at the next dinner party. So the model says yt equals yt minus 1 plus a random error. So today equals yesterday plus a random error. This week equals last week plus a random error. This month equals last month plus a random error. Now the AT are uncorrelated. So that once we know the last period's value, we just add a random component to it. Now we'll see, we're going to simulate some long random walks. And what happens in a random walk is you get long periods of it's going up, it's going up, let's bet on it's going up. And then sudden and unpredictable dramatic changes in direction and increasing variability. So non-constant mean, non-constant variance, and we got two problems. Regular time series methods won't help. Now, let's pause. Now, we will use the term white noise. So we haven't used that before in regression. We just call them random errors. In time series, they're called white noise. And I'll let you Google Wikipedia and look at the historic reasons about why we call that white noise. So something is white noise if it has zero mean, constant variance, and no correlation over time. In other words, white noise exhibits no predictable pattern. What's the best prediction of white noise? 0. The mean is 0, and the last value is independent of the next value, so 0 is our best prediction. Here's 5 random walks: red, green, blue, brown, and turquoise. I use the same program to generate each of them. And if you're in the red thing, you're going, oh, mate, look at that, it's going up. And then if you're in the turquoise one, it goes down for a while and then it goes up. Basically, a random walk can pretty much do what it wants. And notice the variability increases a lot over time. So if you look at the start, at time 0 to 100, the variability is this. At time 900 to 1000, the variability is much higher. Random walk means you just walk off in a random way. So if you were to try and simulate this by walking, is you would walk to a point, and at that point you've forgotten completely where you came from, and you would walk a random amount in a random direction. Please don't do that at home. This is the SAS code to generate those 5 random walks. I've put that in a text file on the eCampus site. I like to use SAS Enterprise Guide because it has these really neat things that I can send the output directly to Jump. So I run the program, produces the output, I send it directly to Jump, and I do my plots. So let's look at some mathematical properties. We're going to do a little bit of manipulating equations. It turns out that it helps us understand how things work. Now, I suggest you get your own pencil and paper and you follow through all the steps. Okay? So the random walk model is model number 1 that says this week's value or today's value, yt, equals yesterday's value, yt minus 1 plus white noise. Now let's rewrite that equation where we're going to make t equal to t minus 1. That makes t minus 1 equal to t minus 2, and it makes t equal to t minus 1. Now, we can take equation 1, that's here, and for this value of yt minus 1, we're going to replace that by yt minus 2 plus at minus 1. So notice we get yt equals yt minus 2 plus 2 of the white noise terms. We can do this again. We're going to replace yt minus 2 by yt minus 3 plus a white noise term. So we get t minus 3 and 3 white noise terms. So if we continue doing this till we get down to y1, we're going to have t white noise terms. So this equation says yt equals y1 plus t white noise terms. That means the variance of yt equals the variance of y1 plus sigma squared plus sigma squared plus sigma squared t times, that's t sigma squared. That says the bigger t is, the larger the time value is, the more variability there is. Good. So, mathematically, the random walk is yt equals yt minus 1 plus random error, or white noise. How do we predict future values of y from the previous value of y? So, in other words, how do we predict yt plus 1? Well, yt plus 1 equals yt plus at plus 1. And at plus 1 is a random error with mean 0. The best estimate of something with mean 0 is 0. Nothing, nada, 0. So the best prediction of yt plus 1 is yt. Okay, what's the best prediction of yt plus 2? Well, that's equal to yt plus 1 plus random error. And we predicted yt plus 1 by yt. And we'll see that this gives predictions of a constant nature. And for those finance buffs, this is called the efficient market hypothesis. Not important for us, but it's just a pointer for folks who've done that. So here is the time series plot and the autocorrelation functions. And what do you see? What I see is these autocorrelation functions down here. What do you see? They all look the same. They all look the same. It says the correlation is very strong positive and it doesn't die out. So when I see this in practice, I get very excited and I go, okay, that looks like a random walk. So one way to cope with a random walk is to use this concept called differencing, which it will be our friend. We will use that every week. So if we difference, that is, instead of looking at yt, we look at yt minus 1, the change in yt. Then that thing we're going to call dt, and if you look at equation 1, we're going to move this over to the left-hand side, and we're left with just at. That says the difference data is made up of white noise, data uncorrelated over time with constant variance. So we've got something that's stationary. We've got something that dt has zero mean and constant variance. So we can model the differences. It's a beautiful thing. And if we have a look at the differences, look at the plots. Look how different, dramatically different they look to the actual data. Now, when you look at those 5 different series, what do you see? I just see stuff that goes up and down, up and down. A positive value can be followed by a negative value. A negative value can be followed by a positive or a negative value, because the correlation structure is here that there's no correlation across time. It's really, really interesting. And remember, how do you calculate the difference? So you take this number and you subtract that number. 6.31 minus 6.24, that's about 0.07. And so we're going to work with the differences. Have a look at the autocorrelation functions of the differences. Well, the autocorrelations there, you have to get up pretty close to look. They're typically 0.03 and 0.04 and 0.05 at best. And we'll see as soon as next week that if anything is outside the blue bands, then it is statistically significant in some sense. And notice none of them poke outside the blue bands. So let's say once we difference the random walk, we get an autocorrelation function where the autocorrelations are really close to 0. So we've taken this really complicated function, which is non-stationary, is non-constant mean, non-constant variance, an autocorrelation function that's very strong and doesn't die out. Right? Remember the autocorrelation function, very strong and doesn't die out. We can't model that. And if all we do is take the difference, we get something that has constant mean, constant variance, and a very small autocorrelation function. Okay. Let's look at our euro exchange rates. If we difference, what happens? Well, wow, look at that. Look at we got the constant mean. We got a few outliers there, But if you look at the autocorrelation function on the right-hand side, the autocorrelations vary. The biggest one is like about 0.02. It's very small, saying once we difference the euro-US exchange rate, we got a series with constant variance apart from a few outliers, zero mean, constant, and an autocorrelation structure which dies out. It doesn't ever get started, dies right from the start. So hence it's reasonable to model exchange rates as a random walk. And here's my random walk. So guess how we do the predictions? We can do them with pencil and paper. It's a beautiful thing here. It's a beautiful thing. So if we want to model the exchange rate on the 28th of July 2017. Our predicted rate is 1.16793. We get 6 decimal places. Well, and where did I get that number from? I got that number from the previous day's rate. Remember, the model is yt equals yt minus 1 plus 0, the random error. So all you do is you go, okay, I'm going to look at today is predicted to be the same as yesterday. Today is predicted to be the same as yesterday. Today is predicted to be the same as yesterday. Today is predicted to be the same as yesterday. We want to try and predict August. We don't have any more values after the end of July. So the 1st of August is 1.180937. That's the first. What are we going to do for the second? We're going to use the same value. So this ends up with constant predictions. This ends up with constant predictions. Now, how do the predictions look? How do the predictions look from the model? If you look at it really quickly, they look pretty good. But we'll see. So, at first glance, the predictions work really well. And this is one of the reasons why I really hate R squared. I just really hate R squared. R squared here is 0.997. Oh my golly gosh, that seems high. But as we'll see, it's fool's gold. Fools! Fool's gold. And the observed and predicted seem to match quite closely. Yeah, at first glance. We need more than a first glance. So here's the observed and predicted through the year from 2000, in the year 2006. I just looked at 1 year because it's really hard with thousands of values to see what's going on. And notice the red is the actual, and the predicted is the blue. And notice the blue follows the red. It's always wrong by 1 day. It's always wrong by 1 day. So in the circled thing, the red is the actuals. So the red goes up and then goes down. What is the blue? The blue stays constant, then goes up and then goes down. Its predictions are off by 1 day. Imagine telling the boss, what's your prediction for tomorrow, sir? Or ma'am, my prediction for tomorrow is the same as today. What about the next day? Well, the next day is going to be the same as tomorrow. And then it's never right? Unless something doesn't change, this is never correct. And here's 2017. And again, you look at it closely, they're off by 1 day. They're off by 1 day. And have a look how we did in August. I think we're going to get fired. I think we're going to get fired. We said it was going to stay constant at this 1.18 and change. No, it's gone up and down. It's gone up and down. So, random walk models are really interesting, very simple mathematics. They're non-stationary. They have non-constant mean, non-constant variance, and their autocorrelation structure doesn't die out over time. But if we take the first differences, we're able to model that very easily. Our model, though, is not very good for short-term predictions. That's why lots of people have lost lots of money trying to predict exchange rates. All right, that's it for this week. What I'm going to do is introduce topic 1 exercises. So what we would have done if we'd been in the same place, live, virtually, or face-to-face, you would have broken out into your groups and done some exercises. Okay, let's pause for a moment. So I've opened up the second PowerPoint, which is a PDF file for you guys called Topic 1 Exercises. Basically, we're going to look at, operator error. We're good. We're going to look at Amazon's quarterly net sales. Mr. Brazos, whatever his name is, just became the richest man in the world. We're going to look at the Austin Airport monthly passenger numbers. We're going to look at this in detail in a later class. And we're going to look at some of their press releases, which really make me smile, as you'll see. And then we're going to look at Niagara Falls monthly hotel occupancy rates. And what you have to do is, for each case study, use plots to decide whether the associated time series has non-constant mean, has non-constant variance, or seasonality. And what I ask you to do is basically reproduce the steps in the class notes. Reproduce the steps in the class notes where we used kernel smoothers to examine the mean, the residuals from the kernel smoother to examine the variability, and the autocorrelation function, as well as those plots to examine seasonality. Now, if you think something has non-constant variance, see whether the log transform works. Remember, with Home Depot and Lowe's, the log transform of sales magically made the variance constant. So this is just really to get you used to using some jump commands. What I suggest you do this on an individual basis. You can talk with folks in your group. And I'm going to go through the answers and discussion as the first online office hours next Monday at 6 p.m. from 6 to 7. So let's look at Amazon's quarterly sales from 2007 to the fourth quarter of 2016. And we want to predict the first 2 quarters of 2017. As you see, every year my job is to update the data. And it makes me cry sometimes when some of my old models don't turn out to be so good, but we'll see. So here's something from the annual report. Net sales in millions of dollars. Have a look at the fourth quarter versus the others. 29, 30, 32, 43. The fourth quarter has the holidays, including Black Friday. They sell a lot more stuff then. Here's a plot. Oh, isn't that magnificent? I'd like to have shares in that business. So, you'll see that there's a variance problem. You'll see that the mean is increasing, and then I'll leave the rest up for you to find out. Okay? But we will develop a model for Amazon. The second one is monthly total passenger numbers at the Austin Airport. From 2002, I started with 2002 because of September 11 in 2001. We'll figure that out at a later date, right through to 2017. We're going to only look at the data in through 2016 in order to predict 2017. And if you go to the website, you can click and see the reports. And here's the data. Looks really interesting. There looks like there's a trend here. And there looks like, ooh, I'm not very good. My blue pen line fit is not very good. And have a look what happened in between. It's at the recession in 2008. We'll see next week and the week after, that's called a level shift. That the whole number of passengers shifted down. And if you look from 2008, it took until about 2012, 2013 to get back to the same level. So if you fit a time series model that doesn't account for that level shift, Oh, not very good. We got a problem. It'll always be wrong. Always be wrong. It'll overestimate in some parts and underestimate in others. Now, I got way too advanced for what you're asked for, right? Let's go back to what you're asked for. All you're asked to do is, does it have constant mean? No, doesn't. It has a complicated mean. Is the variance constant? Well, I'll let you decide that. And is there seasonality? I'll let you decide that based on the plots. That's all you need to do. You don't need to get any more fancy. What we do next depends on the answers to 1, 2, and 3. It really does. I can't tell you how important the fundamentals are. And let's look at Niagara Falls monthly hotel occupancy rate. It's something as a kid I've always wanted to go, but never been. Occupancy rate. And there's this great Canadian website. In the US, it's hard to get hotel data. People want to charge you for it, but in Canada, they provide it for free. And here's a plot. Oh! That shows the occupancy rate is as low as 25% and is as high as more than 90%. The mean looks relatively constant, doesn't it? Over the big picture, but seasonality seems like it's there. You can go in January, the place is empty. They might even close some of the hotels. I don't know. You go in the summer, you better have an advanced booking. So, there we go. What I hope is a gentle introduction to time series. We've gone just over 1.5 hours. I expect when you play this back and you follow the steps, it should take you 2 to 3 hours to get through that. And then it should take you an hour or two to do the 3 exercises. I look forward to talking with you on Monday. For the folks in Houston, our thoughts are with you. Speedy recovery for you and your family and all of your getting around, getting to work, getting home sorted out. In the meantime, if you have any questions about the lecture, please post them online. If you have any question about the exercise, please post that online. I look forward to talking with you on Monday. Bye-bye for now.